All right, here's a video covering stuff from Class 8, Kinetics of Particles, Work and Energy, and Conservation of Energy. I'm not going to go through the entire lecture. This is just going to be a couple examples to help you do the homework. All right, so moving along through here, I've put them together. Instead of writing these out, I'm going to just narrate the solution to this. All right, so we have, this is a problem from Benson Tung's book, the second edition. We have a massless rope that's connected blocks A and B together. And there's friction, a coefficient of friction. The static and the dynamic, I guess they're using mu subscript D there for, instead of mu subscript K. Is equal to 0.6, and the mass of A is 10 kilograms, and the mass of B is 20 kilograms. We're going to assume that this thing actually moves. We could do a static analysis to see if it overcomes static friction, but we could skip that step here. We'll just say that it does move. So differently from Newton's second law, in work and energy problems, it's best to define a state. So we have state 1 and state 2 here. Let me get a pen out here, and I guess I like green. Okay, so this would be state 1 right here, and this is state 2. And then, of course, we'll write over, and here we're also showing state 1 and state 2. And so one of the very first things that we want to do when looking at this, if there's a potential energy change, which there is here, we want to define a datum. And we could actually define that anywhere, but there's usually pretty convenient to pick where the potential energy is going to be 0 and consider that the datum. So sometimes that could be state 1, sometimes it could be state 2, but it's usually good to use a strategy just to save a couple steps. But you could pick it down some arbitrary place. The only problem is that if you pick it up too high, you might end up with negative potential energy. But I like to keep potential energy as a positive thing, so I just pick the lowest spot. Here's the basic equation that we use for doing work and energy parts. We have the kinetic energy and potential energy, and of course this is the energy in the beginning, and then this is the work right here that's being done to it, whether it's positive or negative, depends on whether work energy is being added to the system or removed. And here is the energy state after, so it's state 1 and state 2. I like to make a list separately and just walk through the thing. For whatever reason, I did potential energy first, even though I wrote kinetic energy first in the equation. We look at state 1. We could say that we have mass times gravity times y1. This should be probably mass B right there. That's specific to it. So mass B times the gravity times the position at state 1. And you could even say B at 1 probably would be, you could say be located at B1 if you want to be specific. There's no kinetic energy because it starts from rest at state 1. And then from between states 1 and 2, the work that's performed with this is going to be negative because it's friction, and friction removes energy from the system. It just makes sense. So it's that times the delta x that's being moved here. And delta x and delta y happen to be equal to each other here. If this was a more complicated pulley arrangement, we might need to use constrained motion to get those set up. And in state 2, we have potential energy is equal to 0 because that's where we picked our datum. And then we look at kinetic energy, and here's a little difference. Here's why I'm showing this problem as opposed to the ones in class. I included this problem because it has 2 separate masses. So we have to get the total amount of kinetic energy in the system. It's one of the useful things in work and energy that we could take multiple particles. There could be other methods where that might be a bit difficult. We actually have to do it in parts, but here we can actually include them together. So we need to get friction as part of this. So we do need to do an FBD and IRD. Truth be told, we're only going to use the Y direction here for the FBD part of it. So you could make the case that you only need to do the FBD. But I think we should just acknowledge the thing is moving. So do both diagrams is the right way to approach it. So you find the forces, some of the forces in the Y direction, they equal 0 for block A. So what we end up finding is that the normal force, and then from the normal force we could find the friction force. So we could write all these things down into this right here. Once again, this is just block B is the only one that's changing potential energy, and stick some numbers in there. Here's a good thing to do. I highly recommend it, is to figure out, well, to do the in-between step and come up with a value right here. For both of these, you could see now where the energy is going, or how much of the energy is going. It's also just good practice to try to figure out if you make a mistake later. You could look at these numbers, but you could also look at these numbers and say, is the problem making sense? My approach to the thing, is it correct? It gives you some insight into the nature of it. So from there, you can see that we need, as I mentioned, you need the kinetic energy of both of the things going on. And if you do that, you can solve for the velocity. So now, what if is a good question in any engineering problem, any problem that you're doing. What if we wanted the cable tension? Well, in order to do that, we actually have to break the thing apart. And we could actually do it in either spot. We could either do it on block A or block B. This is block B. And so we could do the whole problem over, but just for that block. And now, once again, the potential energy, because we define this datum, the potential energy at 1 is going to be just the mass of block B times the gravity times the Y position. Now the work that's being done to it is the cable, because this is an external force with the way we've drawn it. And it's going to be times the distance that the thing moves, and it's negative. And you're going to ask, why is it negative? It's negative because the force is going upwards, whereas the motion's going downwards. Since they oppose each other, this is energy being removed from the system. And now we have the kinetic energy at state 2. Okay, at kinetic energy state 1 is 0 because it's not moving. At state 2 it is moving, but it's only the kinetic energy of block B. And so we put those things in there, and now we're able, because we know the velocity, we just found the velocity, we're able to get the cable tension. So if you're asked in a problem like this, what's the cable tension? Quite often what's necessary to do is to do the problem first with both pieces, and then do the problem again with separating the cable out. Now, once again, we could have done after this, we could have done block A only, because right here, once again, we could have we're going to have friction though work being removed from the thing, and we're going to have the tension work also as part of it. So it's interesting that you could see how that works. All right, so, and no pun intended, work. So here is another example. I like this example because there's one thing is a connection between Newton's second law, or a problem that could be done in Newton's second law and be done in work energy. And also just as an overall problem, whether it's in Newton's second law or work energy, it's good to see the effects of changing the things. Because if you look at the nature of the problem, what they're asking here, what they really essentially want you to get out of that is that a 100-pound load in this scenario does not have the same effect as a 100-pound force, because the mass of as a nature of this load right here is going to affect the acceleration of the system, and inevitably the velocity of the system. Which we'll see here in a second. And you could also see right here where we've taken two different weights onto here. The difference between them is the same as the 200 and 100, but now it's 2,200 and 2,100. So working through those. So I'm going to do part B only. I believe we could do part A if we wanted to. Let's see. Yeah, we could do that, but we might have to do a couple other steps. So let's just look at part B. Okay, so here's the fundamental equation that we're going to use. Once again, the kinetic energy and potential energy, the work done, external work, and the kinetic energy and potential energy. So here is scenario 1. I like to draw, once again, the location after at state 2 of the thing. And you'll notice that there's two different weights that are moving, and both of them are changing their potential energies. Just as a strategy, I'm going to make the two separate datums, one for block A, one for block B. It's just going to make my life easier. So I start marching through the thing. It starts from rest. At the beginning of this, the potential energy is all going to be block A. All right, so I'm just going to take block A, and I'm going to say at state 2 that block A's potential energy is 0. So, and the way I've defined block B, its potential energy at state 1 is 0. And then we'll see here in a second that it will be its potential energy will be having that be non-zero at state 2 as drawn. There's no external work being done to this. There's not any friction going on. There's no outside forces, so that's 0. The kinetic energy is going to be of both of the masses, all right? So once again, here's two masses in part of the thing. So we're going to have the same, we're going to have a potential energy. You notice that the velocities are going to be the same. Once again, these could have a different velocity if there was like more of a complicated pulley system. And then potential energy of 2 is going to be where B has risen up. So you write these things out here, and you could see, once again, you could see the in-between steps right there, that we have 2,000 foot-pounds, that's the units of energy in US units, and 1,000 foot-pounds right here. So you can see what's really taking place is the kinetic energy and the velocity, because of that kinetic energy, is coming from that this trade-off between potential energies at the beginning and potential energy at the end. And so we're able to get a velocity from that, which matches Newton's second law. Notice that in Newton's second, if we were to use Newton's second law, what we do for part A is that we would find the accelerations of the thing, and then to get the velocity in part B, we would use kinematics and be a constant acceleration, kinematics, to be able to get this velocity after a 10. But because that we're using work energy, velocity is a lot easier to get. It comes right out. We look at situation 2 here. And now the kinetic energy, once again, starts at 0. The potential energy, okay, for A is going to be the same thing as it was in scenario 1. But now we're going to have this external work being applied. That's between 1 and 2. And because the force is going downwards, but the motion going upwards, once again, that's going to be negative. And we'll see. Okay, right there it says the same thing. And the kinetic energy, again, is only going to be of mass A. So that's really what's going to be fundamentally, it's going to be different, is there was not as much mass to resist the motion for the kinetic energy. So, and then the potential energy is 0, because that's where we define the datum. So we put the numbers in there, and I went ahead and used my 2,000 that I had up above, just down here again. I didn't mean to cross it out. What we're left with is we have a velocity of 17.94, noticing that it's more than scenario 1. Why is it more? Because there's less mass to resist the motion, right? It's really up in here that's going to be the difference between these two problems. There's also a difference in potential energy going off. So this one resists the potential energy as well. So here we go, scenario 3, where now we're going to have the same kinetic energy of 0 in the beginning. Now there's going to be potential energy here. No external work. Once again, the kinetic energies are going to be the total kinetic energy, and then the potential energy is going to be more at the end. And you'll notice here, though, that the trade-off between here for potential energies is going to be larger, right? No, but the difference between them is going to be the same. Let's see, is that correct? Let me double check on it. I believe so. I know that's simple math, but we got 2110 times yeah. So it's still 1,000 foot-pounds difference. I could have done that in my head probably, between the potential energies, but it's really this mass right here that's changing. And you'll see that the larger mass generates a much smaller velocity at state 2 there. Okay, so looking back up at this, noticing, I think actually I do, I include this at the end. Okay, so here's the summary between them that you can see from in scenario 1, we have 14.65. In scenario 2, there's not the potential energy change is is I guess more. Yeah, there'd be more potential energy change because there's no block for state 2 to have potential energy, but also the amount of mass that's being moved is the resistance to the motion isn't as large. And in scenario 3, we don't have as much. We have more mass. Same amount of potential energy change, but we have more mass. So this is a good example of what's actually going on to try to conceptually in the work energy problems. But it's also a good problem to compare Newton's second law in the work energy. So that's all we have.